Welcome to our first video on chapter 6, and chapter 6 is about complex numbers, and section 6.1 is on definitions and algebraic operations. Right, so a bit of background on complex numbers. Now we know that if we have an equation ax squared plus bx plus c equals to 0, where we have non-zero a, b and c to be real numbers, we know that to find the solutions we can use this quadratic formula, and we will have real solutions provided that delta, which is b squared minus 4ac, is greater or equal to 0. And in the case where delta is less than 0, then we will not have real solutions. And if we think about it, even when we have a cubic equation, ax cubed plus bx squared plus cx plus d equals to 0, where a is not equal to 0 and b and c and d are real numbers, then there's a complicated formula that we have, and it will involve it might involve square roots of negative numbers, and so it will have the sort of same problem as a quadratic equation. And this is where the motivation to invent complex numbers came from, and the man who invented the complex numbers is an Italian mathematician called Girolamo Cardano in 1545. So we are going to define a complex number and then look at some properties. Right, so the definition of a complex number. And a complex number is an ordered pair of real numbers z, which is equal to ab. So it's written in this form to just show that this is an ordered pair. And then the real number a, the first number here, is the real part of the complex number. And then the real number b is called the imaginary part of the real number, the complex number z. And then we can write the real part as re of z, and then the imaginary part of as im of z. And then we denote c by this blackboard C to denote the set of all complex numbers. Right. And then we need to know when two real complex numbers are equal, and that is definition 6.1.2. So two complex numbers z and w are equal if and only if the corresponding real part and their corresponding real parts and imaginary parts are equal. Right. And then how do we add complex numbers? And that is definition 6.1.3, and it says if you have got a z and w, then the sum of z and w is the complex number z plus w, which is, so we add the real parts and then the imaginary parts like that, and the product of two complex numbers is of this form: zw becomes ac minus bd, and then ad plus bc, like that. And so let's just look at an example to see how this addition and product of complex numbers work. Right, so suppose you've got z, which is 2, 5, w, which is minus 3, 2. Then we can see that the real part of z is 2, the imaginary part of z is 5, and so forth. So if we want to get z plus w, then we say 2 5 plus minus 3 2, and then we just add the real parts and the imaginary parts, and then we get minus 1 7. And the product of zw, then we just employ this rule that we have here, and we get minus 16 minus 11, right? So let's look at some properties of complex numbers. Right, the first one is commutativity of addition, and it tells us that z plus w is equal to w plus z for all zw in the set of complex numbers. And then for associativity, we know that the set of complex numbers is associative with respect to addition of those complex numbers. And then we also have that there exists an additive identity, and the additive identity is 0 0, right? And then there's also the existence of additive inverses. So for any z, there exists a minus z, which is a complex number, such that if you add the 2, then you get the additive identity. Here the brackets are supposed to be like this, right? And for commutativity, we also have commutativity of multiplication. We had commutativity of addition in number 1, so we also have commutativity of multiplication. And we also have associativity of multiplication. And then we also have the existence of a multiplicative identity, and the identity is the complex number 1 0, and that's that. And then we also have this distributive law of addition, of multiplication over addition, like that, right? So let's look at proof. So we're going to do a couple of proofs for these, and then the rest will be left as an exercise. So proof of 3, so existence of an additive identity. So for any complex number z which is equal to ab, we can see that if we say z plus 0 0, it is going to be equal to a plus 0 b plus 0, which is ab, which is equal to z. And so therefore, by the definition of an additive identity, it means that 0 0 is the additive identity of the set of complex numbers, right? We are going to look at proof of 6, and 6 is the associativity of multiplication. So zwy is equal to zwy, like that, right? So suppose you've got 3 complex numbers, z, y, and w. Then using the rule, we know that zw is going to be equal to ac minus bd, and then ad plus bc. And so therefore, if we want to find zwy, then it means we are going to apply the rule on the vector zw, which is equal to that, and y, which is equal to that. So we are going to say, so we get the first component here times the first component of y minus the second component of the second component of zw times the second component of f, and so forth. So it's just employing the rule that we have, and so we get that. And then if we then expand this, then we get ACE minus DBE and so forth like that. Then what we also know is that if we look at WY, then using the rule for a product of two complex numbers, we can see that WY becomes CE minus DF, CF plus DE like that. So if we then say Z times WY, so we are multiplying Z and then what we have here, then we get something like that by just employing the rule on product of two complex numbers. And then if we expand, we get that, and we can then rearrange these elements, and we will be able to get to ZWY. So here, once we get here, this is the same as what we have there, and so therefore we know this is equal to that. So that's how we get to that. Right, let's look at the proof of 7. What does 7 say? 7 is the existence of multiplicative identity. So we want to show that if we take this complex number, it's and multiply it by any other complex number, we get that that any other complex number. And so for any complex number z which is equal to ab, if we say 1 0 times z, then we do the product of complex of two complex numbers, and we get this is supposed to be minus, right? So this is supposed to be 1a minus 0b, and then 1b plus 0a. So there's no comma here, it's a minus. And we'll see that we just get AB in the end, which is Z. So therefore we have shown that 1 0 is indeed a multiplicative identity, or the multiplicative identity for complex numbers. And then the rest of the proofs are left as an exercise. So we will continue with our video, but that is all for now. Thank you.